All right, open up your book to section 8-2. We're on page 388 in your book. The title of this section is the composite argument property and the linear combination property. We've already talked about the linear combination property, so we'll deal with the composite argument property in this section or this lecture. The objective is to derive a composite argument property expressing the cosine of A minus B, the quantity A minus B, in terms of cosines and sines of just A and B. And then we want to be able to use it to express a linear combination of cosine and sine as a single cosine with a phase displacement. So we've tackled the second half of this objective already. We're going to deal with the first half now. All right, so let's start out with an example here. And the question that we're being asked here is whether or not the cosine of 58 degrees minus 20 degrees is equal to the cosine of 58 degrees minus the cosine of 20 degrees. In essence, this is kind of wondering, does this cosine have this distributive property almost? We could distribute cosine to each of those arguments, each of those angles, and then take the difference of those two cosines. So let's grab our calculator. This is not something we're going to be able to do without a calculator. So grab your calculator and let's see what we get. We're just going to punch in what we see on the left side, punch in what we see on the right side, and see if they're the same. So we've got the cosine of 58 minus 20. Now this is in radians, so let's switch our calculator over to radians. Or sorry, it's in degrees. So we're currently in radians. Let's switch over to degrees. So we get 0.788. And if we take the cosine of 58 minus the cosine of 20, we end up with definitely not the same thing. Let me just grab a picture of that. So the answer here is just big no. These are definitely not the same thing. It would be really nice if this was just a distributive property here. Just write no after this. Those are not the same thing. It would be really nice if that was the property. That would make it really easy to rewrite the cosine of the difference of these two angles here. But unfortunately, that's not the case. Those two are not equal to each other. So then the question is, well, what is the property? If I have the cosine of 58 degrees minus the cosine of 28 degrees, can I rewrite this in terms of just the angles of 58 and just the angle 20 degrees and deal with just the sine and cosine of just those angles alone? And the answer is yes. The answer is the composite argument property. So what exactly is the composite argument property? Well, here is the composite argument property. It says that if you have the cosine of A minus B, like we just had 58 degrees minus 20 degrees. Turns out that that's equal to the cosine of A times the cosine of B plus the sine of A times the sine of B. Notice that we're able to take what we have over on the left, which is a difference of two arguments there, A minus B, and we're able to rewrite it in terms of just sines and cosines of A or B, one of those at a time. That's what we're trying to do. Get rid of the composition of arguments that we have on the left and rewrite it as just the single arguments over on the right. We could grab our calculator and verify that this is in fact the case for that example we just saw there with 58 degrees and 20 degrees. But remember, that only shows that this property works for those two numbers. What about for 59 degrees and 20 degrees? What about for 60 degrees and 20 degrees and so forth? Well, in order to show that it's true for all angles, we're going to have to prove this. So that's what we're going to tackle next. Let's see if we can prove this property. So the composite argument property says that the cosine of A minus B is equal to the product of these two cosines plus the product of those two sines. So what I want to do is sketch these two angles, A and B. And what you're seeing here in front of you is a quarter circle. We could do this on a unit circle here, but this is just the quarter unit circle. And it Certainly could be the unit circle here, but I'm just saving some space here. So for the purposes of this proof here, we're going to sketch this in the first quadrant, but realize that we could sketch these angles anywhere we want. In fact, I'm going to also sketch angle A to be the larger angle. But again, technically it doesn't say that A and B have to be of any size, particular size. It doesn't say that A has to be greater than B or anything like that. But I'm going to mark angle A, let's say, as this angle right here. So this will be our angle A. And then let's mark angle B. We'll call this angle B here. So this is angle B. And in particular, what we're looking at over on the left side of that property is the cosine of A minus B, the angle A minus B. So the angle A minus B is this angle right here. That's A minus B. Now, in particular, what we're interested in on this sketch is I want to find this distance here between these 2 points. In fact, I'm going to call that distance D. And we do have a distance formula that allows me to find the distance between 2 points in the coordinate plane. But to do that, I need to know the coordinates of these 2 points. Now, one thing that we do know is that these 2 points fall on this, it's a quarter circle, but the unit circle here. So that means that the length of each of these lines is 1, the distance from the origin to that circle. So I'll mark each of those as 1. And we do also have the angles indicated that they are A and B. So we have angles and we have, in essence, that distance. All right, so the question is then, can we write the coordinates of those points in terms of that distance and that angle? The answer is yes. We just got to go back and refresh our memory perhaps. Let's do that by going back to the definition of our trig functions. If we mark a point UV here in the coordinate system and we measure the distance from the origin to that point and call it R, and we measure the angle there in standard position, we'll call it theta, then we know that we can find what u and v are equal to in terms of r and theta by using our trig functions. In particular, we know that the cosine of theta is equal to u over r. That's our definition for cosine of theta. And I can, in fact, solve that for u. U is equal to r times the cosine of theta. And that's what I want to know, is I want to know what is the u coordinate there, the x value of that point. That's what I'm trying to do with this quarter circle over on the left. We can do the same thing for sine. The sine of theta is equal to v over r, so that means that v is equal to r sine of theta. Okay, so with that, if I know the r value and I know the theta value, I can write the coordinates of this point then. So the r value in both cases is going to be 1. And the theta value, in the case of this red point that I've got marked here, this top point, that angle is not alpha, it's A. So this is going to be the cosine of A, because r is 1, so it's 1 cosine of A, or just cosine of A. And the y value is going to be 1 sine of A, or just the sine of A. There we go. We can do the same thing for the other point. Again, I can name its x value as 1 times the cosine of b, or that's just the cosine of b. And the y value is 1 times the sine of b, or that's just the sine of b. All right, I guess one last thing we should write down just as a reminder for ourselves is how do we find d? Again, we said that if we have 2 points in the coordinate plane, we have a distance formula that finds that distance for us, but let's refresh our memory here a bit. D, remember, is equal to the square root of, I'm going to write it this way, as x2 minus x1 squared plus y2 minus y1 squared. If I have 2 points in the coordinate plane, x1, y1, and x2, y2, then I can find the distance between them using this formula. In fact, we're actually going to find what d squared is equal to, and we're just going to do that so that I don't have to keep writing this square root down. So if I square both sides of this, I'd end up with just x2 minus x1 squared plus y2 minus y1 squared. All right, so instead of finding what d equals, we're going to find d squared. All right, so let's write down what d squared is equal to? D squared is equal to, it's the difference in the x's squared. So on my sketch up above here, my x's are the cosine, so I'm going to have the cosine of A minus the cosine of B squared. And then I add on the difference in the y squared, so that's the sine. So the sine of A minus the sine of B squared. All right, so now I got a little bit of algebra here I'm going to do. I've got a binomial. Actually, I got two binomials here. We're going to square each of those and see what we end up with. So when I take cosine of A minus the cosine of B and square that out, remember you're going to get a trinomial. There'll be a middle term that shows up here. So you have cosine squared of A. It'll be a minus 2 times the cosine of A cosine of B. And then plus the cosine squared of B. So that's what I get when I square out that first binomial. Let's do the same thing for the second one. Actually, the second one's the same thing, but it's in terms of sine, so we should be able to do that. I've got sine squared of A minus 2 times the sine of A sine of B, and then plus the sine squared of B. All right, so let's reassociate these terms that I've got here. I think let's see, we've got cosine squares, we've got sine squares. So let's take and combine these this way. I've got a cosine squared of A and a sine squared of A. Let's put those two guys together first. So this is equal to the cosine, oops, it's a parenthesis, not a C there out front. Cosine squared of A plus the sine squared of A. And I think you might see why I wanted to combine those two, because hopefully that's refreshing our memory of a property we've seen, cosine squared plus sine squared. That looks like a Pythagorean property we've talked about. So let's do the same thing with these cosine squared of B and this sine squared of B. Let's put those two guys together next. So I've got cosine squared of B plus sine squared of B. And then the last two things I'm just going to write down. You could possibly factor something out like the -2, but I'm going to write them down the way they are. So 2 cosine of A cosine of B minus 2 sine of A sine of B. And now let's use our Pythagorean properties here. That is, this guy right here is equal to 1. And this guy right here is equal to 1. Sine squared plus cosine squared is equal to 1. So actually by writing those down in this form or associating them this way, it was really nice. So actually I've got 1 plus 1 is what I have here to start with. So we'll write that as just 2. And then the stuff at the end there, we've got 2 cosine of A cosine of B minus 2 sine of A sine of B. All right, so there we go. That's what d squared is equal to. D squared is equal to that guy right there. All right, now what I want to do is take and redraw this angle A minus B. Let's take this angle A minus B that we've got right here, and let's rotate that. In this case, we're going to rotate it clockwise so that I can get that angle A minus B in standard position. I'm not changing the size of that angle. Of course, as I rotate this around, this point here is going to move, and it's going to become actually right here on the x-axis. And this point up here, this red one, will also move. But again, the distance between those 2 points, D, should stay the same because this angle is staying the same. So let's sketch what that would look like. So on another quarter circle here, we can move this one up here a little bit. All right, so let's re-sketch this. I guess I'll try to sketch these in the same colors that I had before. So when I rotate this counterclockwise, this red line is going to come down and that blue line is going to come down. The blue line is going to sit right on the x-axis. In fact, maybe I'll sketch that one first. That's where the blue line lands. And the red line, I don't know if it's going to be exactly the same angle, but it was about this right here. The red line would rotate about there. And then the angle between these is still going to be the angle A minus B. Again, as I rotate, I want to make sure I preserve that angle so that this distance between these 2 points is still D. All right, so now let's find the names of these 2 points. The names of the points are going to change because we've rotated this. Let's start with the easy one. The easy one is down here on the x-axis because that's x equals 0, y equals 1. So that's just the point 1, 0. That's the easy one. And the other one, well, the other one's not too difficult because we've now gone through the work of figuring this out, that if I know the distance from that origin to that point and I know the angle, a minus b, I can write this in terms of r cosine of the angle, theta, and r sine of the angle theta. So let's do that. So it's 1 times the cosine of a minus b. That's just the cosine of a minus b. And then r times the sine of a minus b. So that's just the sine of a minus b. There we go. We got our 2 points now. And we're going to go through and do the exact same thing that we did up above there with calculating what d squared is equal to. Again, the only reason we're using d squared here is just so that I don't have to deal with writing that square root out over time. And eventually we'd want to get rid of the square root anyway, so we're just getting rid of it from the beginning. So d squared is equal to the difference in the x's squared, so that's the cosine of a minus b, minus 1 squared, plus the difference in the y's, that's the sine of a minus b, minus 0. That's actually going to be pretty nice because I won't have a binomial there to deal with. That square is pretty easy. We're going to go through and square this out just like we did up above. So you got a binomial when you square it. Remember, you get a trinomial here. So we got cosine squared of a minus b, and then minus 2 times the cosine of a minus b, and then plus 1. And over here on the right, when we square that, we're just going to get a sine squared of a minus b. And now, once again, I think we want to combine some things. I think what we did up above was a nice hint as to what we want to do here. When I see that I got a sine squared plus cosine squared there, that looks pretty sweet. I'm going to go ahead and write it with those associated together, but you could just replace them with what they're equal to in one step if you wanted to. But I've got cosine squared of a minus b plus the sine squared of a minus b. And then I guess I'll write this as minus 2 cosine of a minus b. And then plus 1 at the end. Okay. And again, we're going to use our Pythagorean property here. Cosine squared of an angle plus sine squared of that same angle, that's equal to 1. And actually, I've got a 1 there at the end, so let's combine those two. So the 1 at the end plus this 1 here will give me 2, and then minus 2 cosine of a minus b. So now, again, this is what d squared is equal to. It's the same thing we ended up with up above. We figured out what d squared was equal to. So now I have 2 things that tell me what d squared is equal to. D squared is equal to this quantity, and it's also equal to that quantity up above. So I should be able to set these 2 things equal to each other since they're both equal to d squared and see what I end up with. Let's see what happens when we do that. So let's take this first one right here. I've got 2 minus 2 cosine of a minus b. And up above, just to refresh our memory, this is also what d squared equals. 2 minus that 2 times the cosines and minus 2 times the sine. So this is 2 minus 2 cosine of a cosine of b minus 2 sine of a sine of b. All right, so now let's simplify this. I guess the first thing we should be able to do is to get rid of these 2's here, right? If I subtract 2 from both sides, I'll be left with this here. So I've got a negative 2 cosine of a minus b is equal to a negative 2 cosine of a cosine of b minus 2 sine of a sine of b. Oh, it looks like each of these terms now has a negative 2 in front of it. If I divide everything by a negative 2, divide by a negative 2, divide by a negative 2, divide by a negative 2, dividing each term by a negative 2. So these will cancel out, this will cancel out, that'll cancel out. And hey, look what we end up with. It's the property we have up above. The cosine of a minus b is what we have over here on the left side. We have the cosine of a, cosine of b, plus the sine of A sine of B. Right there is our composite argument property for the cosine of a difference, cosine of A minus B. This property right here, by the way, we're going to see in the next example here actually, this property right here is where we get the linear combination property that we were dealing with in the first half of this section. So let's take a look at an example here. Example number 2 here on page 392. It says, express 7 times the cosine of theta minus 23 degrees as a linear combination of cosine and sine. So to express this as a linear combination, we're going to just use the property that we just came up with, our composite argument property, to get there. So I can replace this guy right here with the property that we just saw on the previous slide there. So I'm going to pull the 7 out front, and I'm going to rewrite the cosine of theta minus 23 degrees. It's the cosine of the first angle, theta, times the cosine of the second angle, 23 degrees, plus the sine of the first angle, theta, times the sine of the second angle, 23 degrees. Sometimes I like reading that off as first angle and second angle when you write that out. Help you remember how to write it. But there's what that's equal to. Let's distribute the 7 through. In fact, as we do that, cosine of 23 degrees is just some number. If I plug that into my calculator, it would spit out some number. Same is true with this guy right here. So let's put the 7 and each of those together out front with these. So we've got 7 times the cosine of 23 degrees times the cosine of theta, plus 7 times the sine of 23 degrees times the sine of theta. And this right here and this right here are just numbers. You could call these B times the cosine of theta plus C times the sine of theta, just like we see with our linear combination property. So let's find out what B and C here are equal to. Let's grab our calculator and punch those in. All right, so we just want to calculate what the 7 times the cosine of 23 is equal to. And we're in degrees. And 7 times the sine of 23 is equal to. And grab those two values. All right, so let's replace 7 cosine of 23 with that 6.444, it looks like. 6.444 cosine of theta plus, and then the 7 sine of 23 is 2.735 times the sine of theta. There we go. We've got ourselves a linear combination of sine and cosine here. It's some constant times cosine plus some constant times sine. That's what it means to be a linear combination. A constant times a variable plus a constant times some other variable. And if I started out with this problem right here, I could use that linear combination property to find out what A and D would be equal to. And we shouldn't be surprised that the A and D you'll come up with are the 7 and the 23 degrees here if we did that. All right, let's take a look at one last example. Example 3 there on the next page, 393. It says solve the equation. We've got a -2 cosine of x plus 3 sine of x is equal to 2. And we're working on the domain from -2 pi to +2 pi. Okay. Now the key here for us to recognize is that first of all, you've got yourself a linear combination of cosine and sine. We have a property that tells us how I can rewrite that linear combination. That's the property we're going to use here in just a minute. The other thing to recognize, though, is that these have the same period. That is, the B value for both of these is 1. Again, it has to be equal periods between these two in order for this property to work. So we're going to use our linear combination property to rewrite this as a sinusoid. So let's figure out what the A and the D value are for our linear combination property. So A turns out to be the square root of a negative 2 squared plus 3 squared. That's 4 and 9. That's 13, square root of 13. And for D, D is the arc tangent. You can start out by saying tangent of D is equal to whatever, or if you want to jump right to the arc tangent. And in fact, if you even want to jump right to the tangent inverse plus the pi n, you can jump to that as well. But we have arc tangent of 3 over a negative 2. And that, of course, is equal to tangent inverse of 3 over a negative 2 plus pi n. All right, so we just need to find out what the value of n is that we need. So think about the quadrant that coordinate point negative 2, 3 falls in. If we were to plot this point negative 2, positive 3, go back 2 to the left, up 3, that puts us in the second quadrant. So because we're in the second quadrant, we're going to have n is equal to 1 over there. And let's actually find what that value is. So let's grab our calculator and evaluate this. Tangent inverse, I had to remember what we needed. Tangent inverse of 3 over a negative 2. We're adding 180, or sorry, now we're adding 180. We're adding pi to that. And I got to get myself in the right mode here. I'm in degree mode here still, so let's switch over to radian mode. All right, so what do we end up with? 2.1587. In fact, I'm going to store that as our value of D here right now. So 2.1587 is our value for D. Or 2.159 if you want 3 decimals there. All right, so now I can rewrite the original problem. Instead of this linear combination of sine and cosine that we started with, I can replace the left side with this sinusoid. It's the square root of 13 times the cosine of x minus, our D value is 2.1587. And we're setting that equal to, up above there, we're setting it equal to 2. So there's the problem that we're trying to solve. Where's that sinusoid equal to 2? This problem we've solved now many times. We know how to solve this using arc cosine in this case to solve this. So that's what we're going to do. Go through that same process. Move the square root of 13 over to the other side. So we have the cosine of x minus 2.1587 is equal to 2 over the square root of 13. Get rid of the cosine by using arc cosine here. So it's x minus 2.1587 is equal to the arc cosine of 2 over root 13. And finally, get rid of your 2.1587, add that to the other side. So x is equal to 2.1587 plus this arc cosine of 2 over root 13. All right, and the last step is to replace arc cosine now with what it's equal to. I'm going to go ahead and write this in its piecewise form just because sometimes we end up with different values of n for each of those. So I'm just going to put it in a piecewise form to start off with. So I've got 2.1587 and then plus the cosine inverse of 2 over root 13 and then plus 2 pi n. We're in radians here, so plus 2 pi n. I've got to figure out what values of n to use there. And then 2.1587 minus the cosine inverse of 2 over root 13 plus 2 pi n, and same story, I got to find out what my values of n are. Now remember that the domain they gave us for this problem was from negative 2 pi to positive 2 pi. So that's 2 full periods of this sinusoid. So I'm going to expect to see a total of 4 solutions here. So I'm going to expect to see two values of n for the top equation and 2 values of n for the bottom equation. 4 total is what I'm expecting to see. The one thing I do need is an accurate sketch of what this looks like, because I've got this phase displacement here to deal with. This phase displacement right there, I'm not sure when I shift that many units to the right, it's hard to tell what's going to happen in terms of the solutions there. So I need an accurate sketch of this. So let's grab our calculator and give ourselves a sketch, and then we can find our solutions. All right, I already stored the value of d there. By the way, you could go to your y equals menu, and you could actually put in the original linear combination of sine and cosine. Since I've done the work here to rewrite this in terms of just cosine, I'm going to do it this way. So it was the square root of, what was it, square root of 13 times the cosine of x minus, and I've already stored to d this value here of 2.1587. And in fact, I'm going to graph the line y equals 2. I probably don't need to have that with it, but I'm going to go ahead and sketch it just so I can see where that's at on my graph. And we want to be in radian mode. We want to change our window to go from negative 2 pi to positive 2 pi. And square root of 13 is, well, square root of 16 is 4. So if we go from negative 4 to positive 4, that should give us a decent sketch of this. Yeah, there we go. All right, so again, I've taken this graph and I've shifted it this 2.1587 units over to the right, and that's what I was trying to figure out, is when I shift that over there, what happens to these solutions here? Is one of these solutions end up out of the window or not? Or more importantly, really, is these solutions over here that are out of the window now, that they got pushed far enough so that they actually show up over here. That's what I'm trying to figure out. So we got ourselves an accurate sketch of this now. In fact, let's grab a picture of that, and we can just draw right on this where our solutions are. In fact, let's make this big enough here for us to sketch on. Okay. So now the task of finding the right values of n to pick here. So again, go back to your phase displacement. Our phase displacement up above was that 2.1587. So here's 1, here's 2. So this is the 2.1587. This is where n is equal to 0, remember? Which means that this high point here is where n is equal to negative 1. So it looks like we're going to get 2 solutions right here. This solution is the negative cosine inverse solution with n equal to negative 1. If we move to the right from there, that solution there is the positive cosine inverse. Here is the negative, and when we go to the right, here is the positive. So it looks like we're going to use n equals negative 1 and 0 for each of these. So I guess I didn't have to write this in its piecewise form, but oh well. We've clearly got all 4 of our solutions marked there now. All right, that is the end of section 8-2.